So we're going to be looking at this wonderful topic on circles. We began on conic sections. So today and a few other lessons that will be coming up, we'll be focusing on this topic of circles. A circle is literally just a set of xy points that are equidistant from a given point. So that means you're going around the circle, around a given point A, B at a constant point distance R, the radius, right? And so the general equation of the circle now becomes x minus a squared plus y minus b squared equals to r squared, which when expanded is x squared plus y squared minus 2ax minus 2by plus a squared plus b squared minus r squared equals to 0. So from that general equation of a circle, if the center is at the origin, that means a and b are 0, 0. That means x squared plus y squared equals to r squared becomes the equation of the circle. If the origin is on the circumference somewhere, that means that at some point x squared and y squared, they become 0. And so, in other words, a squared plus b squared minus r squared equals to 0. So x squared plus y squared minus 2ax minus 2by equals to 0. If we still have that, and then still we have the x-axis at the circumference, then x squared plus y squared equals 2ax. But if instead y-axis is on the circumference, then x squared plus b squared plus x squared plus y squared equals to 2ax. So that really kind of paints a picture around that general equation of a circle. So let's keep going on. So if we normally look at the Euclidean x-y space and the x and y are 90 degrees to one another, if we ask ourselves that what if x and y are at an angle omega shown here, and we still have a circle described by points x, y, and the center being a, b, with respect to x and y coordinates, then we can do a couple of things. One is we can recreate an x and y prime equation that are perpendicular to one another. As we see here, x prime is still coincident on the original x-axis, but then y prime becomes something else. And so if we re-express the coordinates of the circle, both the center and the points on the circle themselves with reference to the x and y prime coordinate system, then this is what we're going to get. We still have the original y component on the new x prime component. So what we're going to have here, the center now becomes a, and then the b component onto that, the x prime component will become b cosine omega, and then the y prime component becomes b sine omega. And then when you go to the x and y, similarly we have x plus y cosine omega representing the x prime, and then y sine omega representing the y prime. So we have a new coordinate system, and now what we can go forward and do is rewrite the equation of the circle using this new coordinate system. So let's see how we may be able to do that. So using what we know now, with the x and y axis being at an angle omega, then we do have the new x plus y cosine omega minus a plus b cosine omega squared, that is for the x prime, and then y sine omega minus b sine omega squared for the y prime equals to r squared. And then you just expand that. And what is important here is now we have x minus a squared plus y minus b squared minus 2 times x minus a times y minus b cosine omega being equal to r squared. Such that if omega is 90 degrees, we still get back to the original equation with the perpendicular x and y axis. So this is really very important. And so moving from there, we can now say, okay, what about if we have a general equation of a circle denoted by ax squared plus ay squared plus 2gx plus 2fy plus equals to 0? Then we can divide through by a and then now recreate this equation. So what we see here is that the center will be minus ga minus fa, and the radius now will be the square root of what we see on the right hand side here, which is the square root of g squared plus f squared minus ac over a. And from these general expressions, there are a couple of things that we may be able to deduce. One is that since the radius is g squared plus f squared minus ac square root over a, it means that if g squared plus f squared is greater than ac, then we have a real circle. That means the square root is real. But if g squared plus f squared is equals to ac, then that degenerates to 0, and instead the circle is a point. But if g squared plus f squared is less than ac, then the circle is imaginary, because in the square root of a negative value is what we're contending with, which is really key. From a general equation of a circle, you can deduce the three facts that we have, whether a circle is real, a circle is a point, or it's an imaginary or non-existent circle. So another thing that is important to denote is that given the general equation of the circle, we see the point C there really not featuring into the coordinate of the center. So if the general equation of the circle just differ by this value of c, or the absolute term, then it means that what is changing is just the radius, and so the circles are concentric. If a is the same, if g is the same, if f is the same, but c is only what is changing between different equations, then you can tell that these equations denote circles that have a common center but different radii. So just an extra thing to be aware about. So this is important to note, and we'll keep building on these facts. So one other thing we like us to look at is the power of an external point relative to a circle, right? So if we have a circle and we do have a point that is external, a point P, whose coordinates is x prime, y prime, then we draw a line such that the line goes through the center of the circle, and we have point B and A touching it. Then the power of that point relative to that circle is OP, the distance OP, minus OA, which is the radii. And so we can see using Pythagoras theorem that that is just equivalent to the distance from the point where the tangent touches the circle to the point P. And so if that distance is t, then the power of that point relative to the circle is t squared. We use pi to denote the power of a point, or the product symbol. And then if that point moves to the circumference, then OP minus OA becomes 0. So the power of this point with respect to the circle, if that point is on the circumference of the circle, is 0. But then there's also another scenario where that point now moves from the circumference into the circle. and we'll see how that changes. So you see right now, if the point is on the circumference, then the power is 0. But when it goes in, then OP squared minus OS squared is equals to OP squared minus R squared, which is, we have to flip, so we have negative of R minus OP times OP plus R. There's difference of 2 squares, so we have negative AP times PB, negative distance AP times PB. And so we have a couple of things. When the point is outside the circle, it's a positive power. If the point is on the circumference, the power is 0. And if the point now moves inside the circle, we see that the power of that point relative to the circle becomes negative. And this is something that we continue. In the next lesson, we'll look at the importance of power of a point and how it does relate to the circle. So this is a very interesting thing to look at. A circle is a very interesting locus, and then we'll continue to build. So if you haven't subscribed to our channel, we encourage you to subscribe. Take time to look at our other videos. We're interested in topics of calculus and other things. So until next time, bye bye.